So today's lesson's on writing and understanding how to form net ionic chemical equations. Now we need to understand these things if we want to understand how to write redox equations, and or if you're taking AP chemistry, you need to understand how to do these because many of the experiments and the lessons are done using aqueous systems, and aqueous systems rely heavily on net ionic chemical equations. Net ionic equations are balanced chemical equations that describe only ion particles that actually take part in the reaction. They are part of a larger balanced ionic equation, and they generally describe reactions that are conducted in aqueous solutions where a precipitate results from the chemical reaction occurring. Now let's talk about these spectator ions here. It says no spectators. What do we mean by that? Well, let's envision you going to a basketball game. You are in the stands as a spectator and you're watching the game. The action for the game is all happening on the court, not in the stands, right? You're just watching what's going on. So two teams start at the beginning of the game with each has a 0 score. During the game, the score changes back and forth until the end of the game when one team has more points than the other team. So there has been a change in the score, and one team has resulted in a winning team, and the other team has a losing team. Now let's transfer that back into what's happening in a chemical reaction. We start with reactants, and over time, those reactants are going to change into something new. Now, when we do it with ions, not all the ions are going to react and form new things. Some of the ions are going to sit around and watch the chemical reaction. Those ions that don't change in their composition from reactant to product are called spectator ions. So I've just given you a kind of a little bit of terminology on the spectator ions, right? They don't partake in the reaction. They just kind of watch and spectate from the side. Precipitation is the process where a solid material forms and then comes out of a solution. And a precipitate is that material that forms and comes out of solution. It's a solid, right? So those are terminologies that we're going to need to know for the next few slides. So what do we mean by aqueous solutions and ions in aqueous solutions? Let's look at the hydration of sodium chloride. So we're basically going to take sodium chloride crystals and dissolve them in water. So my sodium chloride is my solute, my water is my solvent. So when we do that, we take this sodium chloride crystal here, which is hard and brittle, that has sodium ions and chloride ions that are tightly packed with a high electrostatic charge. And when we put them in water, the crystal does a couple of things. It starts to break apart into smaller and smaller crystals until eventually the crystals break down and dissociate into sodium ions and chloride ions. And around it is this aqueous system, this water system. So no longer do we have sodium chloride pieces, we actually have sodium ions and chloride ions dispersed in all the water, right? So we don't have sodium chloride particles, we have sodium ions and chloride ions. So that's what we mean by aqueous sodium chloride. So let's look at a microscopic visual of what happens when we put sodium chloride in water to form a sodium chloride aqueous solution. So here's my salt crystal as it starts, and it's in dry, and I add water, and my water's here. Water's a polar solvent. In other words, it has a more positively charged end and a more negatively charged end due to the electron shift in the molecule. The molecule itself is neutral, but the electrons are just more to one side than the other. As we put the water in there and it starts to break apart the crystal, at the end you will see that the sodium ion, the metal ion, is surrounded by water molecules, where the minus end of the water molecules of the dipole is associated with the more positive sodium ion. So in reality, we don't have sodium ions one by one. We have these hydrated sodium ions that look like this. and this is represented by the chemical symbol right here. So again, if this was potassium instead of sodium, it would be K plus aqueous. On the same side, we have the chloride ion. Now the chloride ion is a minus charge, so the more positive end of the water molecule is going to be attracted to that. And so you can see here, and again, when the ion is dissociated and hydrated, it looks like this in solution, and that's what we're representing by the Cl minus. Aqueous. We're going to look at an example now with all these things to try to get a better understanding of what we mean. So we're looking at silver nitrate aqueous reacting with sodium chloride aqueous as my two reactants, and then we're going to form silver chloride. That's going to be a solid, that's going to come out of solution, and then the other part of the solution is going to have sodium nitrate. Now we know what a complete chemical equation is. We know what a complete ionic equation is. Now we're going to separate these into their ions if they get separated. And we've done that right here. So we've separated this down here into its ions. So then we just have silver ions for my silver nitrate, nitrate ions for my silver nitrate, sodium ions for my sodium chloride, chloride ions for my sodium chloride. Now we're yields or forms. Now look at this, AgClS. So this is a solid. No, it's not written in ionic form. There's no ions here. It's a solid material. And then my last one is aqueous, so we write that as sodium aqueous ion, and then nitrate ion aqueous. So the spectator ions, we're going to figure out which one of these are the spectator ions, and at the end of the day, we're only going to care about what things form my precipitate, and that would be my silver aqueous ion and my chloride aqueous ion, giving me solid silver chloride. Here is a model to help visually explain what's going on. So I've written the chemical equation up here again, and then I've broken it down into the ionic equation, and that's here, right? And again, this is not in an ionic form because it's a solid, it's no longer in solution, right? And then I've taken these ions and I've put them in a reaction vessel. So my reactants are over here, and what we have as far as products here. Now visually you can see that everything is a nice ion over here, and they're well dispersed and they're bouncing off everything, and they're all in the container as ions. As we do the reaction, we can see that some of the ions are still in solution, yet some of the ions have come together and formed a new structure, silver chloride. Okay? So we've taken a bunch of ions here, undergone a chemical change. Some ions are left around, and then some ions have formed a new material from the ions in the reactants. And now we're going to understand in the next slide what's happening chemically. Okay, so we're back to our model, and now the goal is to write the net ionic equation. So if you look on my thing here, my ionic equation into my net ionic equation, I have to cancel same on each side. So what does that mean? So basically, let's look at our visual here of our reactants and products. So here's my reactants. All the ions are in solution, and in the products, only some of the ions are still in solution. Some of the ions have formed this new material, the silver chloride crystal, right? So we know that there's been a change because we don't see this silver crystal on this side here. We don't see it over here. We see it here only. We see things that looks like they have made up this silver chloride crystal in here, but we don't see it in this exact format, right? So how do we use our equation to tell us that, right? So we're looking for the same on each side. What I mean by same, it has to be exactly the same. So if I have NO3 minus aqueous on the reactant side and the product side, then it's the same. So therefore it hasn't gone through a change, a chemical change. So we're going to exit out. So cancel on each side. So we're going to exit out. So let's start from the beginning. Here's my silver ion. I need to have this exact silver ion over in my product side. So I'm looking at my product side and I don't see silver ion exactly. I see silver with the chloride in the solid form, but that means it's no longer an ion form in the aqueous solution because it's solid, therefore it has come out. So there has been a chemical change here, and it says cancel same on each side. These aren't the same, so we're not going to cancel the silver. And we're not going to cancel the silver chloride. What about my nitrate? So nitrate aqueous, I'm looking for nitrate aqueous over here, and I see it right here. So it says cancel same, so we're just going to X it out. And we're going to look at next at my sodium. So here's my Na plus aqueous. I need to have exactly Na plus aqueous on this side. I see Na plus aqueous over here, so we're going to cancel that out. Right? And the last thing we're going to look at is my chloride. So I see Cl minus aqueous. I need to see exactly Cl minus aqueous on my product side. I don't. I see Cl again, but it's not Cl minus aqueous, so, or the ion of chlorine aqueous, so we're going to keep it. And so what I'm left with is things that look like they've made up there's part of the chemical reaction. So we have our silver ion. We have our chloride ion in aqueous solution, and we have our silver chloride solid that comes out of solution, all right? And so what does this represent? This represents this, and these represent, the chloride is the yellow dots here, right? Those are the yellow dots, and the silver is the red dot, right? So those represent that. And in the end, when we write our net ionic equation, all we're going to be doing is the chloride comes down here, whereas there is written that way. The silver is written here, and the silver chloride solid is this part of the chemical reaction. So hopefully that helps that. You can see it visually, and you can use your cancel technique to also get the same equation. All right, so let's do another one for practice, except this time we're not going to use a visual model. We're just going to do it the cancel way, like I showed you at the end of the last slide. All right, so here we go. First thing I need to do is I've got to balance it, right? So balance it, then I can see here silver as 1 here and 2 here. So I got to balance the equation. So I'm going to balance the equation now. Okay, I've balanced the equation. I've given you the new coefficients in red. If you don't know how to balance the equations, then you should either learn that or review it, right? Or ask your teacher to help you understand how to do it. So next thing I have to do is I have to separate my balanced equation here into an ionic equation. So I'm going to do that now. Okay, so there's my full ionic equation, and you can see here I have 2 silver ions. Remember, when you do this, since you have 2 AgNO3s, you actually have 2 silvers and 2 nitrates, right? There's my nitrate polyatomic ion, my anion. So I have 2 silvers and 2 nitrates. So when you write your full ionic equation, you got to make sure you have 2 silver ions and 2 nitrate ions. And the same thing here, when you have sodium sulfide, you have a 2 here. That means there are 2 sodium ions in sodium sulfide, so we have to make sure we list it down here. All right, so I've done that. Now we're going to go and look for the same again, just like we did before. All right, so again, here's my silver aqueous. We have 2 of those. I have to find exactly this on the other side, and I'm looking and looking and looking, and I don't, but I do see silver sulfide here. It has silver in it, but this is not the same as this, so I'm going to keep it. Next thing we're going to do is the nitrate. I need 2 nitrate aqueuses. So I'm going to look for here on my product side, and there it is, right there. So we're going to X those out. So we X them out, 1 and 1. And then we're going to do the same thing for my sodium. I need to see 2 sodium ions here, aqueous. I have 2 sodium ions here, aqueous. There's supposed to be an aqueous listed there. So we're going to put that down here. That's X out. And what are we left with? We got one more to look at. We have sulfide ion here, aqueous. Again, I don't see the sulfur here. I only see Ag2S, so we're going to keep that. So my net balanced equation, or net ionic equation that's balanced, is the following. We have to list it as, we're going to do it as 2Ag plus aqueous plus S2 minus aqueous yields silver sulfide solid. All right, so that's my balanced net ionic equation. Okay, if you followed any one of my videos, you know that I always give you a time to do it on your own, and then you can check your answer at the end of the video. So here's that time. So what you're going to do is you're going to take this chemical equation here, and you're going to do these steps to get it into the final net ionic form. So when you're ready, you're going to stop the video, write all the information down, then restart the video when you're when you want to check the answer. So stop the video now. Okay, so again, here we go, and I'm just going to quickly go over that. Here's my balanced equation. Here's my ionic equation. Now there's a little bit of an error here. This should say lithium plus. I'm just going to write the plus there right now. And then everything else is good. Should be good. Again, these all should have written AQ underneath them in your answer. I don't have enough room here to write everything in AQ. So anything that's listed here is ion in aqueous system. So again, if you quickly did your check and cancel thing for the same things on each side, you would see that the nitrates go away and the lithiums go away on each side. And then what you're left with is exactly what's written down here. Here's my 2 aluminums. Here's my 3 carbonates in the aqueous form, and I form aluminum carbonate solid. And so if you got that, and you got all this other stuff correct, you're pretty good to go. You should you understand what's going on. If you still struggle with this or still have questions, come find me or ask your teacher.